So, all right, let's start up with today's topic with Mr. Nikhil Kashyap, who is an experienced machine learning engineer who has been providing enterprise-wide transformation programs and solutions to several organizations. Okay, so hope you guys will have a great session with him today, and thanks for staying with me. Hi, Nikhil. I think you can take over from here.
Yeah, thank you, Numpy. Okay.
Have I stopped sharing my screen?
Yes.
Okay, thank you.
Yeah. Hello, everyone. Hope you guys are doing well. Um, so it's been a really good weather here. Where I stay, it's been raining since morning, and it's a perfect weather to stay at home and get cozy. So we'll start with today's webinar. We'll explore neural networks and what are neural networks and how to build it from scratch. So I hope you guys can see my screen. If yes, type yes in the chat box. So I know that I'm audible and you guys can see my screen. Okay, thank you. Okay, right. So this neural networks, have been successfully applied to the broad spectrum of data-intensive applications. Right from your face recognition in your iPhone to the futuristic self-driving cars, neural networks has made its way into many fields in the last decade. Neural networks is also seeping into many other fields. The businesses are adopting neural networks into their daily business decision making. There is a broad horizon of opportunities for the applications of neural networks in the coming decade as well. So, what is this neural network? You might have heard about it as some kind of magic voodoo, but it's not. It's a computational model, and in today's webinar, we will demystify it. So, this is a basic representation of the neural networks, and you can see here that neural network consists of something called neurons. All these circular objects are called the neurons, and the connection between these neurons are called weights and some biases connected to each neuron. The first layer is called the input layer, and the last layer is called the output layer, and the rest in the middle are called the hidden layers. You can think about neurons as something which holds a value, like a number. You know, once have read all the input features to move forward through the network called a forward pass, we iteratively use a formula to calculate each neuron in the next layer. So this is something what we would use. So here W is the weight and V is the bias and A is the activation of the neuron. Uh, this takes us forward until we get an output. We use this through layers and layers until we get an output, and we measure how good it is. The We measure how good this output y hat is using something called a cost function. Just before the cost function, we will dive into something called an activation function. So this basically is a SIGMOID activation function, and there are a lot of other activation functions like ReLU, TANH, leaky ReLU. But here we'll take the sigmoid, and this activation function tells us if the neuron should activate or it should not activate. Basically, that's it. That's what the activation functions do. So this is a graph of the sigmoid activation function. And if you see if the value calculated is closer to 1, the neuron fires, and if it is closer to 0, the neuron is basically dead. Um, so now what we'll do is some we'll after get um, until we go forward, when we get the output, we measure how good this output y hat, which you can see here, is by a cost function c, which is given by this equation. This is nothing but your regular mean squared error equation. There are a lot of cost functions, and this is one of the it is most often used and one of the simplest cost functions you have. Once you have the cost function, we go back and adjust the weights and biases so that we optimize the cost function. This is called a backward pass. This is how we tell the algorithm that it performed poorly or good. We do this for every observation from our data set. So here, L is the layer, and C, this is basically a partial differentiation of the equation. To update the network, we calculate, the gradients, which is small updates to individual weights of each layer. Whatever you can see in the first equation is the equation which we use to calculate the gradients. Once you have the partial differentiation of the cost function, you update the weights by simply subtracting it with the learning rate times the cost of the particular weight, which is given in the second equation. So this is the basic understanding of feed forward and back propagation of the neural network. Uh, so if you guys didn't follow any of these, don't worry about it. We'll take an example and walk through all the concepts we just discussed. So we already have established each neuron has an activation A, and each neuron that is connected to a new neuron has a weight W. As I told you before, think about these neurons as something which holds the value. So this input layer is something which is given to us by the data set we input. So what about how do you calculate the values of the rest of the layers afterwards? What we'll do is we'll consider this example here, and let's say 0.3 and 1.0 are the inputs given to us by the data set, and weights here 1.1 and 2.6 are randomly initialized. Now, how do you calculate the value of this particular neuron, which you can see here? So what we do is we multiply activation by weights and get a single neuron in the next layer. That is, so if you can see from here, so weight of the first neuron and the activation of the first neuron, weight of the second neuron and the activation of the second neuron, up to in neurons, if you multiply it and if you add, if it's a summation, so if you add it, you get the value of the new neuron. So in this particular case, so what you do is it is 0.3 into 1.1 plus 1.0 into 2.6. So which gives you to 2.93. So if you didn't understand what we are doing here, before I showed you the equation, this particular equation in the end, which you can see. What we are doing here is we are calculating w dot a. So that's what we are doing right now. So in this particular equation, the other things which we have here are the bias and the the something the sigmoid function which is there. Um, so we'll park bias for now, and we'll get into it later. But we'll see what sigmoid is here. So sigmoid is activation functions, as I told you before. It activation functions determines based on the value it receives determines it should fire the neuron or it shouldn't fire the neuron. That's all. Its function is, and in this particular example, what we are considering the sigmoid function, and the equation is given by 1 by 1 plus e power minus x. So now what we do is whatever we calculated from before, we wrap it around it. So whatever we got from multiplying the weights and the activation and summing it, so that will be our x, and which you can see from the equation, the third equation in below. So we substitute it there, and if the value we get is near to 0, then the neuron won't fire, and if it is near to 1, then the neuron fires. Now coming to bias. So bias is trying to approximate where the value of the neuron starts to be meaningful. So you would try to add or subtract a bias from the multiplication of activation and weights. So what we are doing here is this is which we already calculated weight and activation, which we multiplied and summed it, and we are adding something called a bias. It's you can it's just a real number. You're adding to it, and oh, now we are wrapping the activation function sigmoid in this case around it, and whatever you get as the value will be the value of your neuron. So what you do is you do this for every neuron, and you propagate forward. That's why the name forward propagation, through layers until you get the output. So let's say we took the inputs. We did all this. We did the forward propagation and everything. Now we have an output. All right. So we have a predicted output. So once you have the predicted output, and because you already would be having the labels, and there will be an actual output y and the predicted output y hat. So now what we are doing is we are comparing you know the actual output to the predicted output, if seeing that if our neural network has predicted accurately. So what we are doing is we are basically in this particular cost function, we are it's we are taking the mean square of it, and we are calculating something called as uh, uh, a cost function. Uh, there are too many cost functions to mention them, but this is something which is very often used, so I picked this. Here, as I told you, y is the actual output, and y hat is the output which is predicted from the neural network. Basically, for every sample n, we start summing from the first example, I is equal to 1, and over all the squares of the differences between the output. We want y and the predicted output y hat for each observation. Um, So once you have the cost function, so what till now what we did was we took the inputs, forward propagated, and we calculated a cost function, right? Once you have once you have the cost function, what you do is um, now we know how the our predicted output, how far our predicted output and our actual output, our desired output is. So what we do is we do something called as back propagation and adjust weights and biases so that we'll optimize our cost function. So now in this back propagation, so what we'll do is we'll calculate something called gradients efficiently while optimizers do the training of the neural networks using these gradients computed with the backprop. So how do you go backwards, right? What we do is we always start from output layer and propagate backwards, updating the weights and bias for each layer. We adjust the weights and bias throughout the neural network so that we get the desired output in the um, output layer. Before we get into how to compute gradients, let's define each of the symbols which we are using so that you can follow through uh, the whole session. So what you do is you know um, I'll give you these these equations. So L so L is for the last layer and L minus 1 is for the second last layer, and L small L is for the layer, and Y is our actual output, and C is the cost function, W is the weight, A is the activation, B is the bias, and Z is the WA plus B, which we calculated before. And so since we have everything in place, we'll get into the back propagation. What I'll do is I'll give you the equations for the back propagations and intuition behind it, so it makes sense to you guys. So these are the three equations for calculating gradient. So what you do is, if you don't know what partial differentiation is, so these squashed D's are the symbols for the partial differentiation. So what you do is you differentiate with respect to when you say partial differentiation of C by partial differentiation of W, you differentiate with respect to W, leaving everything, treating everything else as without differentiating the rest of the variables. That's what you're doing. So what we'll do is these three are the equations to calculate the gradients for the for our back propagation. So we have our first equation. So our or partial differentiation of C by partial differentiation of W. With AL is the last layer, what you go, what you have, and you calculate it for W with that given equation, and then you go with B, the bias, and you calculate it, and then you have activation. You calculate the activation of the previous layer, that is our AFL minus one, and using this particular equation, you calculate these these values. But one thing you need to remember that these equations just measure the ratios of how a particular weight affects the cost of the function which we want to optimize. So, after calculating the weights and bias, you update them by using the following equation, uh, which is you update the W of the layer L with W of L minus alpha is the learning rate, which you would define. It's one of the hyperparameters, and you multiply with it with the 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 gradient of the weight you calculated. So this is nothing but your gradient descent. So if W is at the right side of the curve, uh, the derivative, you can visualize it from the graph on your right. So the W is at the right side of the curve. The derivative, that is the slope, would be positive, and hence you would subtract from the equation to move towards the global minima. So hence the equation makes sense, right? So if the W is at the left side of the curve, and then the derivative, that is the slope, would be negative, and hence would add to W in the equation to so that you would move towards the global minima. So this is if you didn't understand it, so let me, yeah, if it's working. So this is what is basically happening. So you are define alpha, and that is your learning rate, and your objective is to find the lowest point. Uh, so so that if it's on the right side, so you subtract, and if it's on the left side, you add. So that's what is basically happening here. And if I have to define, if I have to, summarize the whole thing, step by step for you. So what you, do is, so the first thing is you initialize the weights to some random number and let all bias be zero. So what you are doing is you're basically initializing weights to random. But one thing for you to know is don't initialize weights to zero. Initialize it to a very small number, something like something like between 0 to 1 or even less, but never initialize it to zero, but initialize bias to zero, and then you start forward pass by using the following equation which we just discussed. uh, you do it for every layer and every neuron, and once you reach the output, you calculate the cost function and see how accurately your neural network predicted, in comparison with your actual, or the desired output. Once you have this, this is where the back propagation starts. And so what you do is you calculate the gradients using these particular equation for weights, bias, and activation, and you um, you know go back from last layer to the first layer, adjusting updating your weights and biases using the equations provided in the last step. This is pretty much without diving deep into the neural networks. This is pretty much the intuition behind the math of the neural networks. Um, you can, if you want to, if you are interested, you can understand how the derivation works. Those are pretty straightforward and pretty simple. You can certainly, understand, how they would work, and this is, but the intuition is same. We can take the example of logistic regression, and you can take the data of cats versus dogs, um, and you can start implementing on top of it and see how it performs. um, you can implement it from the scratch. So now, before I get into the you know um, the coding part, if you guys have any doubts, you can you know you can share it in the chat. Oh yes. If I'm not pronouncing your name, Pershing. Yeah, hi Pershing. Why the sigmoid functions is the most used? Um yes, it's because it's very popular, and it's very simple, simple to implement, especially um, you know with the if you have to uh, um, what do you say, if you have to decide if the neurons has to fire or not. It's a simple, right? Closer to one it fires, and lesser closer to zero it doesn't fire. It's pretty simple to understand. It's pretty simple to implement. So sigmoid function is it's most commonly used. But if you come to the computer vision, uh, like the hardcore computer vision, like the face recognition or anything else, so what you use is you would yeah. So when sorry, so uh, you would use something called as ReLU for the computer vision problems. So that is very popular among the computer vision problems. Um, it's not that you should just stick to sigmoid functions. You can use other functions also, other activation functions also, which I'll be sharing the notebook with you guys, and I encourage you guys to take the explore with the notebook, and in fact implement ReLU, TANH, and see how it performs. How it performs when you compare it with the sigmoid function. Yeah, Rajesh. So if I'm not audible, so yeah, I would like to know that. So Krishnaveni is will be able to understand neural network only if all these partial different. Okay. Uh, so I can. Okay. I didn't for because it will take me some time. for me to implement, for me to explain the derivation of, all these partial differentiation. So I didn't include it in the scope of this webinar. But if you guys are all up for it, then, I'll, I can explain it to you guys. I'll take some examples, and we can walk it together, and with the time we have left, we can explore it. So if you guys are up for it, then I won't be able to have much time left with explaining the code. So if you guys are more interested in how to understand, uh, you know how to derive these equations and how to understand them, I'm up for it. So if you could. Yes, yes, Pershing. So, in the next, I'll be explaining you how to implement all these concepts, um, you know, with the simple Python code, and how to go about it. As we'll be taking an MNIST handwritten data set. It's a very simple example, and we'll take it and we'll implement it together. How the implementation of neural network on Scratch? Oh no, when I say from scratch, I'm not using Scratch. So it's, I'm implementing from ground up using Python. That's what I meant. So I'm still waiting for, if you guys are up for, some digging into a little more deeper into math, as Krishnaveni asked here. So if you guys are up for it, I can, we together can explore some math behind some derivations of how we arrived into those partial differentiation. Okay. Okay. I didn't expect that. Uh, Many of you guys will be interested in knowing the math behind it. So okay, we'll explore the math behind it. Give me a second. I'll see what I can. Okay, guys, I'm really sorry that I actually didn't prepare for, because I never expected that you guys would be interested to dig deep into math, but I'll try my best to explain you guys, you know, uh, step by step how to arrive at the equation, which we just discussed. Um, okay, sorry guys for, keeping you waiting. So this is something which, uh, can you guys see my screen? Okay, thanks. So this is something from my personal profile, my github.io page. This is some notes which whenever I do the course, I jot down some notes. So recently, I start publishing whatever the notes I start taking. So this is off from there. Um, so what we'll do is, we will just follow through this. Um, yeah. Um, so we'll jog through this together, and if you have any doubts anywhere in between, put a post your question here so that we'll try to explain it together. So what we'll do here is we'll take this particular example of cats versus dogs. All right, so we'll implement the logistic regression as a neural network, which is a binary classification. So linear regression, as you know, is used for binary classification. So what we are doing here is this is a 64 cross 64 image of the cats. So if you get the output as one, then it is a cat, and if the output is zero, then it's a non-cat. And the RGB values, which you can see here, are the matrices which you have it here. Will be of the dimension 64 cross 64, and because it is RGB and red, green, blue, so the length of the input features will be 64 cross 64 into 3. This makes sense to you guys, right? You have 64 cross 64, and RGB is the depth. So the length of the input features is 64 cross 64 into 3. Does it make sense to you guys? If yes, please type yes. Okay, cool. Okay. So, from the image above, this is exactly, the rest is exactly what I explained. Um, So this n of x means now, n of x means the a dimension of the input feature, or feature vector. Uh, let's not worry about this notations, because down I'll be explaining it. Let me see what we have. Yeah, can you see now? Yeah, I think, yeah. Okay. So, this is something which I already explained it to you before. The nodes, represents, the inputs, activations, and, you have outputs, and weights is a, the edges is a weights and bias. So, this is something which you already know, which we explored it. So now coming to the logistic regression. So if X is a picture, Y hat tells you what is the chance that it is a cat. So what we are doing is we are talking in probabilities now. So if X is the pixel values of the picture, then Y hat tells you what is the chance that that it is a cat or not. So when we are talking in probabilities, we can write y hat is a probability of y equals 1, as we established here. When the output is 1, it is cat, and output is 0, it is not cat. So probability of y is equal to 1. What is the probability of y is equal to 1 given x, right? Uh, this is a pretty simple probability, where x belongs to the real numbers. Uh, and we have our weights, which belongs to real numbers, and our bias, which belongs to real numbers. Now we just explored, in the PPT, that uh, what I explained it to you, the forward propagation, where sigmoid is our most commonly used activation function. Uh, we are, this is a WX, it's the same thing, but only thing what we are doing here is we are just transposing it. Um, so it's the same equation what we saw before. Don't panic about it. It's the same thing. Um, so this particular equation, sigmoid of W transpose X plus B, can be larger than 1 or negative values, right? So in logistic regression, the output should be right. We just established that we are dealing with probability now, so the output should be between 0 to 1. So that's why we use the sigmoid function to normalize the output. We even explored the equation of our sigmoid function, in before, and this is some interesting, uh, you know, um, uh, thing which we'll be exploring here. So, what if, yeah, Z equals a large positive number, right? So Z is this. If you guys have a pen and a paper, please write it down, so that when we visit it later, you won't be confused. Z is this. So what if a Z is a very large positive number? Then we are substituting in this equation, that would be approximately equal to 1 by negative infinity. All right, so e power negative infinity is 0. So one, so this whole thing will be 0, and 1.1 is 1. And if Z is a large negative number, then e power minus or minus infinity, you are substituting here, e power infinity will be infinity. So 1 by 1 plus infinity is 1 by infinity, which is 0. um, I really hope for you guys it's making sense. Did you just, okay, thanks, Aditya. So you guys know what Z here is, and we are dealing with the probabilities here, so it is between 0 to 1. And what happens if Z is a very large number, and what happens when Z is a very small number. So once you have this, we have been talking about cost function, right? So this is, till here what I explained you is, the forward propagation. So you do this for every neuron in the every layer again and again until you reach the output. So this is, something which is fun. So now we have the output, and which is the predicted output y hat, and now we have the actual output, which is y. Um, so taking these two, we, in the if I take the, yes, here we did the mean squared error, will be our cost function. So logistic regression has its own cost function. As I told you before, there are a lot of cost functions, and the logistic regression has its own cost function, which is, given by this particular equation. Uh, so you can just write it down, because we will be referring it, a lot, so that, we'll be referencing to it a lot, so that, later when there is a substitution or anything, you just, okay, you just have to look it up in your notes and you get the understanding. So it is given by this equation. So once you have this equation, so we'll again explore when y is equal to 1. So you're substituting y equals 1 here. So what happens when y is equal to 1? You just substitute. So 1 minus 1 is 0. So you're multiplying, this whole equation goes, and you're just left with this, because y will be 1, so you won't be writing y again, right? So I really hope this makes sense to you guys. You're just substituting 1 to this particular equation. That's it, nothing more. We want log y hat to be very small, and y hat to be large. Um, so I'll tell you why it's in this way, but we'll substitute in the equation and we'll see. Then this will make sense to you guys. So from equation one, that our equation one is this. Okay. So we know that y hat lies between 0 to 1. So we substitute it with 1, and now we are substituting it with 0. So once it is 0, so you're substituting here. So this whole value becomes 0, and 1 minus 0 is 1, and you're left with only this part of the equation, that is this. So in this particular thing, so we want log y hat to be very large and y hat to be small. Again, we know that from the first equation it is between 0 to 1. So we'll just skip that. And loss. Okay, so this is something which you guys need to know in terms of the terminologies when we say loss function, when we refer it to as a loss function, and when we refer it to as a cost function. So loss function defines how well you're doing on a single training example. All right, cost function defines how well you're doing on an entire data set. This pretty much makes sense, right? So cost function is the summation of the loss functions, right? So so the equation for the cost function is given by this. This is not the cost function for everything. This is the cost function given to for the logistic regression which we are exploring here. So this equation represents this. All right. So this whole thing, instead of writing this whole thing, we are just writing it here, because it is superscripted with I, because when we say loss function, it is with training example. So it's just how well it is doing with first training example. You calculate the loss function. So next, how well it is doing well with the second training example. You do it with till for M training examples. That is all your observations in your data set. So this equation gives you the equation for the cost function. So instead of writing this, when you substitute it with the rest of the equation, this is how your cost function looks. This is the whole equation of your cost function. What we did was we simply substituted this value with the RHS from equation 3. That's all we did, and this is your overall cost function. So now coming to the gradient descent. So we calculate. So till now we did the forward propagation. We explored what loss function is. We got to know the equation. We explored what what is the difference between loss function and cost function is. So we got the equation for our cost function. So once you have this, so this is your gradient descent. Uh, this is you optimize, so you use gradient descent to optimize your cost function. So it's an optimizer. So what your gradient descent does is you do this repeatedly, you perform this operation repeatedly over and over again. So W is, we know that it's a weight, and alpha is a learning rate, and we have J of W comma B. So what we are doing is, I have written a capital B, that, but don't worry about it. It's a partial differentiation. So we are, it's a partial differentiation of this particular equation. All right. So this is the partial differentiation of this particular equation, with respect to W. So, that's what you're doing. So for W, you're doing this, and, as I told you, alpha is the learning rate, and, the same thing. So, if W is on the right hand side, so the slope, the derivative would be negative, right? So you are minus of minus, so it will be plus. So you'll be you'll be coming down, and if it is on the left hand side, so you'll be subtracting, you'll be adding to this, and you'll be reaching your global minima here. All right. So this is which we discussed in the PPTs before. So you did it for you took the partial differentiation with respect to W for the weights, and you do the same thing for the bias with the respect. You take the partial differentiation with respect to B, for the bias, and you update. So you're basically updating W and B here. Yeah, oh, right. I have the correct equation here. As I told you, this is a partial, differentiation. You're performing partial differentiation on this particular, equation. So we have, where do we have it? Yeah, so now we have established our, how to update our weights and biases. So if you have any doubts so far. Rajesh, are we calculating the boundaries in this case in the sense, what do you mean? We are not integrating, we are differentiating. Oh, you mean in the summation with this? Yeah, there are bounds, right? So when you say I is equal to 1, it is the first training example. M is here, the last training example, the mth training example you have.
Sorry.
Yeah, Rajesh, tell me.
Yeah. No, not that slide. Actually, you are in that cat application slide.
Right. Okay.
There we were taking 0 and 1 for y to calculate below that. So here the model inputs are 1 for cat and 0 for not cat. So
No,
that
no,
means
no.
we.
It's not the model input. It's the model output. Once you feed this image into the model here, the
Hmm.
output, if it is one, it's a cat. The output,
Hmm.
if it is zero, it's not cat. That's what we are
Okay,
trying to
okay,
establish.
okay. Okay. I got this doubt because below this slide, you have mentioned something that y can be between between 1 and 0 also. So that is why I asked that. Okay.
Yeah, yeah. Y is between 1 and 0, right? Because
Yes,
we are
yes.
taking the probability. That's why we are using the sigmoid function.
Okay.
So that we squash the value between 0 to 1. If it is closer to 1, we declare it as cat. If it is closer to 0, we declare it as not cat.
Oh, so actually, what we are doing is we are pushing it to be 1 or 0. So,
Right.
okay, okay, okay. Because I thought it represented something like fuzzy logic also. That is why I just wanted to get
Oh,
clarified
no,
on
no,
that.
no, no. Yeah, 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 yeah. Oh, yeah. So I hope, I cleared your doubts.
Okay, okay. And one more thing. And
Yeah.
why do we have to use partial differentiation in this case? Is there any significance for this method, or I couldn't understand that for a
Oh,
long time actually.
no, no. It's just uh, you don't do the complete differentiation because when you are differentiating, because you are updating only W, right? If you differentiate without considering
With
B.
respect to only one denominator. I mean, we are differentiating with respect to only one denominator. So that is why we are going only for a partial differentiation, right? Okay.
Hello.
Ah, yeah, yeah, yeah.
Yeah, yeah. It just got muted. Okay.
Okay.
Once if you fully differentiate, you'll be having the values of B also. So you won't be, truly calculating the value of, updating the value of W. So you'll be having elements of B also, which you don't want that, right? So that's why you partially differentiate with respect to W and update W, and we partially differentiate with respect to B and you update B. You got the
Okay.
idea,
Okay.
right?
Yeah, understood. And
You don't.
okay.
The thing is, you don't need to, understand, in-depth math to this.
Uh,
If you just have, you just need to have the intuition. So if you have that math intuition, it's pretty straightforward.
yeah,
And
yeah.
in fact, that is true for implementing the neural network also. You don't need to know the heavy math. You just, if you have the intuition, you can play around hyperparameters to get increase accuracy.
Okay, okay. And one more doubt. We are actually calculating the loss function, and the summation of the loss function is the cost function, right?
Exactly, exactly.
And what is the physical meaning of that loss function and cost function with respect to the application? In, for example, in the case of cat application, what is sorry in the
Right.
case of cat application, what is
Mhm.
the why do we have to calculate the loss? And actually, the application is we just have to find out whether it is a cat or not, right?
Right. Oh, for
Mm.
human brain, it is very easy because we see the picture and we say, oh, okay, it is a cat, it is a dog, it is a cow, right?
Okay. Mm-hmm.
But see, the thing is, what you need to understand is the input here, is once you see the cat, if I ask you how do you know that it's a cat, you'll say, oh, look at it ears, look at its eyes, right? But the machine won't understand in those terms. Machine will look at the pixel values here. So
Okay.
once I say it, you need to understand that right now we are dealing with numbers. We the cat picture has been reduced to numbers, which that is here, this
Okay.
RGB
Mm-hmm.
values, which we have this.
Mm-hmm.
So once you're dealing with numbers, so that's why you do all these things. That's why you need the cost function. That's why you need the loss functions. Because now you're dealing with the numbers, and you're trying to make sense out of those numbers so that the machine learns out of it and tries to classify it as a cat or a not cat.
Okay, okay. I mean, let me be blunt in this way. I mean, so
Okay.
what I mean is, what I thought is actually we are bound to lose some data during the process that we do. So I thought that that could be a loss. So in that case, we are calculating the loss and summing it to the cost function maybe. So that is what I understood in the beginning. Maybe there could be a reason why we are calculating this, but that is why I just wanted to get clarified. Yeah.
Sure, sure. Yeah, yeah, yeah.
Okay, okay. Because I have one project going on,
Oh, okay.
so I just wanted to learn. I just want to know whether I can use this neural networks for that, or how to go for some other. Method. So that is why I just wanted to know
No,
in
the
detail.
thing is, what we are trying to understand here is we are understanding the neural networks from scratch. All right. So I'll,
Oh,
after this, I'll show you the code, and we'll go through it together.
okay.
But the thing is, you don't once I probably have written like nearly 100 lines of code to
Hmm.
implement this. But once you have, thanks to all the open source contribution, TensorFlow, PyTorch, and everything, you
Okay.
don't have to write that much of code, and all these things are taken care by the framework itself.
Okay. 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 Okay.
Yeah,
Okay. Yeah. Thanks. Thanks. Okay.
yeah, yeah. Thank you, Rajesh. uh, okay. I think we are, yeah, we'll get right to it. And I hope that you guys are clear about all these all the doubts you had. So we'll get into the logistic regression gradient descent. So we have these equations. So we are establishing z is equal to, I'm sorry, I missed x here. It should be w transpose x plus b. I have missed it here. Don't, so please, if you're making a note of it, it should be w transpose x plus b. And we have y hat, which is sigmoid of z, which we calculating here, and we have our loss function here. So once we have it here, we can say, if we have two input features, x1 and x2 here, right? So let's say we have two input features, and w1 and w2 is our weights, and bias is here is our b. So we will take this example, and we'll see go through the forward propagation here. So z will be w1 x1 plus w2 x2 plus b, which we already saw on the slides also. And once you have z, we are wrapping it around a sigmoid, and you are getting the output z here. Z, and you apply sigmoid, and you're squashing the values between 0 to 1, and you are getting it, you're getting the output there. Uh, what we now we have the output y hat, and once, as we know, once we have the output, we take the loss function. We calculate the loss function, uh, which by uh, so in gradient descent we modify so values of w and b, which we discussed before. After we get L of ay, we calculate the derivative, so which we discussed it this even in the slides to get the loss. In this particular thing, we calculated, how we saw how to update weights and biases previously. What we are doing here is how to update the activation A. So that's what we are exploring here. So that's why a partial differentiation of the cost function with respect to A, you get the, uh, you know, um, you get the how you'll know how to update the activation function. So from equation 10 here, so we are just performing a partial differentiation. If you guys know how to perform partial differentiation, so it will be easier for you to follow. If you don't know how to do it, don't worry about it. Sit back, relax. We'll come back to it later. We know with dA represents the partial differentiation. What we are performing here is this, and we know that log x with respect to x is 1 by x, which for doing it here. So and log of 1 minus x with respect to x, this is 1 by minus 1 by 1 minus x. These are the pretty much the derivatives which you already know. So what we are doing is we are just substituting these values here and simplifying it. So I won't get deep into it because for guys who already know how to do partial differentiation, it must be it will be very easy for you. So you just plug these values into this, and you have this equation. Now we have dA, which is once we have the the activation, so now we can go backwards, right? So we'll be using this equation which we established in the slides also. So from this we can show that the above equation is equal to a minus y. I won't go into it. If you guys need the proof, how big is the proof? Yeah, if it's only this much, so yeah. So we can show this particular equation is equal to a minus y. So the partial differentiation of L with respect to Z can be expressed as this partial differentiation of L with respect to A, partial differentiation of A with respect to Z, and a partial differentiation of A and partial differentiation of Z turns out to be this particular equation, and the derivative of the sigmoid is this particular equation. So we defined before Z of sigmoid of Z is equal to A. Substituting in the above equation, this equation we get d of A by d of Z is equal to A of 1 minus A, and this is pretty much substituting the values. So from equation 13, we can write equation 13 as equation 14. So you can here just equation 13 is this. So you are substituting the values here, and if you just simplify, you get a minus y. I know I rushed through this. For some of you guys, you might find it hard to understand. If you don't know what partial differentiation is. So it's basically, what we just did is a few things which we already knew. We just took it and we just plugged it in, and rest of the thing is simple algebra, which we reduced it. So that's why we say that this particular can be equation can be represented as a minus y. We'll take that and we'll perform rest of the operations for now. Once what we did was we were taking just for one example, that is that's why we are going for our loss function. But what we can do now here is we'll go for all the m examples. That is that is our cost function. So we'll start with this is just a pseudo code. Most of you here can easily understand this. We'll initialize J with 0, dw1 with 0, dw2 with 0, db with 0. For I is equal to 1 to m. So this is our forward propagation. We did it, and this is our output y hat. So we have it here. So once we have the output, what we do next? We calculate the cost function, right? So once we have the cost function, d of z is which we just established here, which is a minus y. We have it here. What we are doing here is we are just updating our you know the value of our weights, w1, and value of our weights w2. If you just forgot what it was this. Till now we did the back propagation. What we're doing is we did the forward. We are doing the back propagation now. So we have we had W1 and W2. So we are updating W1 with this particular equation and W2 with this particular equation. And DB, we are again incrementing the bias with this particular equation. So now we are, after going through all this iteration, now we are updating the whole thing here. And this is, just LaTeX equation. If you don't know what it is, we are just establishing W1 is equal to W1 minus alpha of, that is our learning rate of dW1, which we calculated here. And similarly for W2 is equal to W2 minus alpha of dW2, which we calculated here, and RDB, which we calculated here, is B minus alpha of dB. So since we have considered only two input features, x1 and x2, so there is no need for a for loop. But when there are more features, we need to use for loop. These are the programming which we'll hopefully we'll get to it later. I know most of you, or even some of you, didn't follow most of this, the later part of it. If you didn't follow, don't worry about it. It's just that we did the forward propagation, we calculated the cost function, and we performed back propagation. That's what we are doing. That's all we are doing. So now, with respect to Python and vectorization, I think I'll just skip this because most of you guys know because you know how to use Numpy and dot product. So we'll come to vectorizing logistic regression. All right. So what you do is we have this equation, right? We have the equation for z, so which can be written in NumPy code as this. So these are basically syntaxes. You guys should already know all this. If I give you the equation, probably you guys should know how to implement it. Because we are establishing all this, for our later, to implement this using Python. So that's what we are doing here. I think I can skip this also because we'll come to one last derivation, which is cost function here. This derivation. So broadcasting in Python is something like here the number b will be broadcast. So if b is equal to 10 and you're adding it with 1, 2, 3, 4, 5, then b will be broadcasted into 10, 10, 10, 10, 10. So you add it, so you get it. You get the correct output. You don't need to worry about the dimension. That's what we are saying. It's something what we something to do with the Python. Right. So here is which you guys were mostly asking. So whatever we did now is to is like the foundation to understand this particular derivation. So once you know this derivation, so I bet you guys can easily implement neural networks. So what logistic regression cost function. So again and again we are writing this equation, we are establishing this. So this is our z value, and a sigmoid of z, we get the output y hat, right? So we have it here, the sigmoid function. So again, we're we are talking in probabilities. Y hat is equal to probability of y being 1 given x. So if in other words, if y is equal to 1, so p of probability of y given x is equal to y hat, and we know that if you get the equation, I mean like the probability of one, the probability of the other will be 1 minus y hat, right? So it's no brainer. It's like your high school math. So once we have established this, so what we can do is we can write equation 1 and 2 as probability of y given x is equal to y hat or y of 1 minus y hat into 1 minus y. That is what we are doing here. So okay. So what we do is once we have this equation in place, we start um, um, you know putting in numbers and see how it performs. So with this particular equation in mind, so if y is equal to 1, so you're basically what you're doing is you're substituting y is equal to 1 here, and 1 minus 1 is 0. We know anything raised to power 0 is 1. So if y is equal to 1, probability of y given x is equal to y hat. If y is equal to 0, probability of y given x is equal to 1 minus y hat. This is also no-brainer for most of you guys. It's pretty straightforward. So what we'll do is we'll maximize log of p of y should give similar result as optimizing. So somehow we have found that if you maximize log of p of probability of y given x, if you maximize it, so it should give similar result as optimizing probability of y given x. So what you're doing is to this particular equation, you're applying log to both the sides. Once you have log to both the sides, this is what you get. So are you guys is it this thing seem familiar to you guys? We just discussed this. So we are already coming near to the actual derivation, which is similar to this. Negative of loss, negative of loss function. So all we need to do is take the negative and put it on the other side. So while training an algorithm, we need to make probability p of y given x large and minimize the loss function. That's the whole point of having our loss function and cost function, right? So it's always a min-max problem. So you minimize the loss and maximize the profit. So that's maximize the accuracy in this case. So all we need to do is minimize this. So equation 4 is this, is the loss function on a single sample, which we just established. So what we'll do is we'll go and calculate it for m samples. That will be our cost function. So the thing is, if you assume that the training examples are identically independent distributed, don't worry about what it means. Then the probability of the examples are just know that this is already an established equation. With using this, we'll derive for for the cost function. So probability of labels in training set is equal to this is just the summation of through samples when I is equal to 1 to m to probability of y of I given x of I. So what you're doing is you're applying log again to both the sides. Log of pi, the big pi gives you the sum, which is I is equal to 1 to m log of p of I, y of I of x of I. So we just established that this is equal to this here, right? So what we are doing is we are just substituting here. That's all we are doing here. So now what you can say is cost of j of w comma b. Here we need to optimize this cost. So to get rid of the negative sign, to make sure the quantities are better scaled. We need to add 1 by m for extra scaling factor. That's how we are adding 1 by m to already this, which this by the way should be sigma of if I have missed it there, if you guys noticed, so it is just sigma of. So this is basically the derivation of the cost function and the loss function. I really hope some of you guys, at least some of you guys, understood or followed through most of it. If you did your partial differentiation back in your undergrad and I never did it, I really encourage you guys to go and brush it up a little bit. You don't need to get in depth. The rest is, as you know, it's just substitution, and you just substitute, and the rest is just the algebra, which I'm pretty sure you guys are, you guys can do it. So this is the equation for, that's how we got these equations. So this, what I have written is something which we established here. So with this equation is particular to this cost function. So that's why it might look, it looks different for you guys. As I told you, there are many cost functions, and here I considered mean squared error. So that's why, the equation might look this way to you. Here we are, we are considering the cost function of the logistic, equation, that is this. So that's what basically we are, we are doing here, and the updating is the same, right? So we did the same thing there also. We use the same formula to update, here also. So this is, your what to say, the derivation of your cost function and your loss function and your forward propagation and your backward propagation also. This is pretty much it's there to understand in the neural networks. If you guys have any doubt, if is cost function is equal to error and backpropagation is equal to field value, it's like control system. Right. I don't know. Yeah, Rajesh. So I don't know. I don't have knowledge in control systems, but I have very limited knowledge from my undergrad. Yeah. This is something you can understand it. As you said it here. If you guys have any questions, you can ask now. Nancy, are we running out of time?
Oh, go ahead, Nikhil. As far as
Because
you'll
I
have
don't
any
know.
doubts, yeah, they can probably you can have Q&A now.
Yeah, I'll have Q&A, and what I'll do is, I'll okay. Before that, I'll just run you through the Jupyter notebook for you guys. So what we are doing here is we are just importing the necessary packages, and fetchml is here. So we are taking it, and we are loading the MNIST data. And what we are doing here is we are separating the MNIST data from x comma y. That is, x will have all the inputs, input features, and y will have all the labels. So I'm just printing the shape of x and shape of y. And here, once you visualize the data, this is how it looks. So while deriving, we considered 64 cross 64 cat image example. This is 28 cross 28. So the first digit is y of 0 is 5. So the pixel values looks something like this for 5. So if you just print it, you'll see, and you can see that it is between 0 to 255 here. because of the RGB values. What we'll do here is we'll normalize the pictures by by dividing it by 255, so that it will range from 0 to 1. So once you have this, that is for the input features, what you'll do is you'll take the Y and do something called one hot encoding. So what it takes is, one will be 1000000, two will be 01000. So you get the idea, right? Three will be 001, and the rest will be 0. So that's how we are converting. We are taking all the integers and converting into vectors. Now this is your regular, split and train and split the data set. Now we are doing is we are implementing the activation function SIGMOID. We know the equation, so this is the equation which is implemented using NumPy, and we have the softmax. Softmax is another activation function which use it for the last layer when you have multi-class classification. In the previous example, cat or non-cat, we took it is only two-class binary classification. So that's why SIGMOID works. But if it is multi-class, you use softmax. And this is you're initializing the number of layers, how many input layers should be there, how many first hidden layers should be there, how many second hidden layers should be there. And as I told you before, you're initializing w1, w2, w3 randomly, using np.random.random. So that's what you're basically initializing here. And forward pass is, as we discussed, this is a dot of w1x plus and w1x, and you're applying sigmoid. So this is RZ, and you're applying sigmoid on it. So this is pretty much all the equation we just went through. That is what using those equations, that's what we are implementing here. And this is your backward propagation. Again, the same thing, all these equations what we went through, that is the same thing what we are calculating here. Once you have it here, so update the parameters, these equations, that's what we are doing. That's what it is being implemented here. And here is the full code. I ran it only for 10 epochs, and you can see the accuracy is very bad, like 13. So what I want you guys to do is share it with you. If you have a notebook, please take a note of it. Play with the epochs and see, how many, increase the epochs. Epochs is here as one forward propagation on backward propagation is equal to 1 epoch. So increase the epochs and see how it performs. 784 is, as I told you, it is 8 cross 28. So that's why it is 784. That will be your input layer. If you change it, you will get the error. You can change the hidden layer. Now this will be hidden layer 1 and hidden layer 2. You can change it as much as possible, as you can, and see how it performs as you change it, and change the epochs as well. And what you can, these are all the hyperparameters which you can here. Instead of sigmoid, as I was telling you before, there is another activation called ReLU. ReLU. So you can get that equation of ReLU and implement it. Just replace sigmoid ReLU instead of sigmoid here, and call the sigmoid function and see how it performs. So pretty much the rest is pretty standard. So you can I actually encourage you to explore all that and see how it perform. How you can how the neural networks perform. So I'll be sharing the notebook with you guys. I highly encourage you guys to explore it. And if you have any doubts, you can. We have a Facebook forum. You can discuss it there. You can post your questions, or any one of us will see, and we'll reply you there. For till now, if if you have any doubts of whatever I explained, I'll take a couple of questions now. If you guys have any questions. Okay, I think you guys.
Yeah, I think everybody's done with this.
Yeah, yeah. So, guys, I'll be sharing the notebook with you all. So, how neural network and machine learning. Okay, so Rajesh, the thing is, you really can't draw the line between data science, machine learning, deep learning. It's like machine learning is the umbrella, and neural networks is a subset of machine learning. If you're talking about classical machine learning, like the statistical models, like your random forest regression and your k-means clustering and all those things, those are not learning algorithms. They don't learn, so that's why there is need of neural networks. Uh, all the optimizers we just discussed now, those are the learning parameters. So that's how the neural network learns. That's I would say a neural network is like a subset of machine learning.
Okay, okay.
So
Yeah, I'll mail it to Nancy, and Nancy will mail it to you all guys, as soon as she can.
yes, we will be forwarding the Jupyter notebook with you all, and you will be able to find the recording on our YouTube channel. Okay, so I'm just dropping in feedback form and registration for October 3rd's webinar session and our LinkedIn page and everything here on the chat box. So kindly take a note of it. Thank you, Nikhil, for doing the presentation today.
Thank you, Nancy.
Yeah, thank you guys. Thank you all for joining us.